This conference will now be recorded.
So, good evening. Today we'll be learning about Newton's third law of motion. So, we have so far learned Newton's first law, where it talks about when there is no external force, that means F is equal to 0. So, there will be no acceleration. That means particle or any object will move in a same velocity throughout, okay, or uniform with uniform velocity, or if any object is at rest, that will remain at rest forever. So second law relates force, external force with the acceleration of an object, okay, or in other words I can say, see, if I just write the mathematical form of second law, dp dt is equal to F external. So external force is a measure of, like, yeah, so external force, if you apply an external force to an object, there will be change in the linear momentum. So that is what we have learned. So see, the second law was dealing with the force, okay, but we haven't talked there about the source of the force, okay. Obviously you need some source of the force or external agency to apply the force, okay. But here in the third law we'll look that the origin of force is actually the object, like the objects which are acted upon by force, they actually themselves is actually the external force is the mutual interaction, it says, okay, mutual interactions between objects. And in the third law we'll look that external force does not appear, external force or force does not appear single, okay, single force does not appear. So what I want to mean is force always appear in pair, always appears in pair, okay. That means if you take two objects, okay, I have that figure maybe, yes. So let me tell you first the statement of the third law of Newton's motion. The fact I was saying is actually given. See, the fact is that there is a force but force does not occur alone. Okay. So in this universe, wherever there is a force, force will be occurring in pair, and that fact was given by Sir Isaac Newton in the form of a law. That is, every action has an equal and opposite reaction. Every action has an equal and opposite reaction. So forces always exist in pair. So one can be called as action, another one can be called as reaction. I'll just give you a specific example. Suppose if we take a spring, if you apply force by your two fingers, suppose this is actually action. This is an action. So what is reaction? The reaction is that the spring also will give an equal and opposite force. I hope you are familiar with this thing. So this force is called reaction. This is reaction. So not only this, in this universe, anything you take, suppose there are two objects, A and B. There are two objects, A and B. So they are in contact, suppose. So if A is applying a force on B, and that force, suppose, so force on B due to A, this is called force on B, FBA, force on B due to A. So similarly, A also will be experiencing a force which will be exerted by B. So this force is called FAB. Okay, and obviously you can see these forces are equal and opposite in direction. So there are many examples in our day-to-day life. I'll take one by one. So in this, according to Newton's third law, every action has an equal and opposite reaction. So any one of them can be called as action, and the other one can be called as reaction. Okay, any one of that can be called as action. Suppose I say FAB is action, and then this can be called as reaction, but these are equal and opposite, so you can write in this way. Okay, now these forces are, see, these forces have some properties. We can just see these forces are not cause and effect. These are not cause and effect. These are not cause and effect. So when you have occurs, they occur in pair. They are equal and opposite in direction, but they are not cause and effect. One we are saying as action, another one is reaction. That is true, but nothing is called cause and effect. Okay. One more thing is that this action and reaction, you can see from here that action and reaction always act on different bodies. Always act on different bodies. Different bodies. In this case, you look the action. If I say the force BA, that is action given by A onto B. So this is action, and the reaction is acting on the other object, that is on A due to B. So this is the reaction. So action and reaction, they act on two different objects. The force of action and reaction cannot cancel each other. This is because action and reaction, though equal and opposite, always act on different bodies. So they cannot make a balance. I hope this you understand. So action and reaction, they are occurring on two different bodies. So that's why action and reaction, they cannot make or establish an equilibrium situation. They cannot cancel each other. So third point was they cannot cancel each other. Okay. So what is action? I'll write once again. Action and reaction are not cause and effect. Number two is action and reaction act on different bodies. Okay, different bodies. How is that action and reaction cannot establish an equilibrium Why? Because action and reaction, they are acting on different objects. So that is the reason. The fourth one is that no action can occur in the absence of the reaction. No action can occur in the absence of the reaction. Okay. For example, in a tag of war, one team can pull the rope only if the other team is also pulling. So pulling is action. But if the other team is not pulling, then see any team has to pull, then the other team also can pull. So this is one is action, another one is reaction. So in this case, so in case of tug of war, you can see that if there is no reaction, there cannot be action also. So we have learned three things. One more point I just want to mention. See, in this case, look, action and reaction is there, and in this case, see your hand, the fingers are actually in contact with the spring. So in this case also, see A, B, they are in contact. Can you give me some example where there will be action and reaction without contact? Yes, I can give you an example. Okay, so what is that example? The example is that gravitational pull. So due to the acceleration G, okay, so which is acting always downward or towards the center of the earth, so any object will be pulled by, suppose I have an object like this, small stone kind of that is pulled by, suppose this has mass m, so it will be having mg force towards the center of the earth, and that is because of gravity. Okay, so in this case we can see the gravitational pull Fg, gravitational pull, but where is the reaction? Reaction in the sense, see, gravitational pull is given by what? It is actually given by R. Okay, R. This is R. It is pulling towards the center of the R. So the gravitational acceleration is actually produced by R. Okay. So R is pulling the object. Suppose here it is having mass m, and this is capital M. Capital M. So the question is whether in this case also there is action and reaction, even though these objects are like Earth and the stone may not be in contact initially, whether they have action and reaction. See, there will be action and reaction both. See, in this case, gravitational pull is the action. What is the reaction? Then reaction will be the force exerted by the stone on the earth. That means earth also, sorry, the stone also will pull the earth, and we know action and reaction will be same, equal and opposite in the, see, if this is a stone, this is earth, so earth is also will be pulled by this mass, small, this small stone, but you may not be believing. So this is reaction. So with the same equal and opposite force, suppose in this way the object has force mg on that, and see this reaction also will be mg, exactly equal to mg. Suppose you have a stone of small m and you are just releasing it from free space, so what will happen? It will just come to the, because of this gravitational pull, it will be pulled down to the earth surface. So the force given by the earth is mg, which is acting downward, this one. And it is, see, according to Newton's third law of motion, the stone also will be applying a force towards it. Okay, so it will be actually pulling the earth, but you cannot believe this, right? If we are also pulling the earth with equal and opposite force, so why don't we see, why don't we feel objects which are released from the top of a floor that is just pulled by earth, so that has certain velocity. Okay, that's why we can understand that, see, some object, if you just leave from your rooftop, it will just fall down easily. So it is a velocity, it has a velocity and acceleration both. So we can understand that there is a force on this, and that is due to gravity offered by Earth. Now, how can I believe that Earth also will feel the same force or reaction exerted by the stone itself? With the same force, it will be pulling. But why don't we see any change in the motion of the Earth? Because Earth is Earth is massive, very, very massive. Massive means what? Mass is very, very great than small m. It is very, very large. So then you might be thinking, what is the problem? If the mass is very, very large, why don't you see the motion of the Earth? Why don't you see the motion of the stone? It is because, see, when we have velocity or acceleration, then only we can have a feeling of any motion. Look, if the force is same Fg, if I divide with this small m, I get acceleration on the small m. Okay, which will be a grade, because this force is great force, a large force. So divide that with mass. So you get the acceleration of that stone. But what about the acceleration of the earth? Say m earth will be very large. So this acceleration will be negligible to zero. Okay, it will be very negligible. So why don't we feel that earth is also attracted by any object in this universe equally? Because the earth, see, in the motion of the earth, we don't see any change. Why? Because the mass is massive. That's why the acceleration, even though the force is equal, but acceleration will be very small, as good as zero. So as I have shown you here, okay, as good as zero. So that's why we don't see any change in the momentum or any change in the velocity or any change in the motion of the earth itself. So that's why we cannot feel that earth also experience a force like this reaction. Okay, anyway, we have learned what is action and reaction. Even if so, in this case, see, there was no physical contact with the earth and that particular object, but still, due to gravity, it is feeling a force towards the center, and the stone also will be pulling with the same force, that is called reaction. Okay. Now what we will do, we will illustrate Newton's third law through few examples. Like I'll take up the first example. This is a very common example. Our books, we are just reading our books and dumping on the table. Suppose such a book is resting on the tabletop, as you can see from here. So what happens? What is action and reaction over here? We are talking about action and reaction according to Newton's third law. So what is action and what is reaction over here? See, on the tabletop when you keep, the weight is always actually acting downward direction or along the direction of the gravitational acceleration. So weight is always acting downward. You can see that this is W weight. Now the floor of the table also will give equal and opposite reaction on this table. Okay, on this table, because table is giving a downward force which is equal to the weight of the book. The same amount of force will be actually given by the flow to the book, and see eventually this is true and this equal and opposite. So weight is actually acting downward, and R is actually called normal force. Normal force here it is reaction. Okay, reaction. So normal force is the force which occur due to, see here, at the contact surface. Okay, contact surface. Okay, see, whenever you are even we are stepping on the ground, so ground will give one normal force which is equal and opposite to our, so equal in that like equal in magnitude and opposite in direction. Okay, so this is called normal reaction or normal force, which is exactly equal to the weight of any body. Okay, we'll talk furthermore when we talk about normal force again. All right, so because of this only, the book on the table is not flying off. Otherwise, they may fly off. Okay, because of this reaction only, they cannot fly off, because this W weight and this reaction, they will be cancelling each other. So neither the book is actually breaking the table nor it is flying off. That is why, because there will be no net force Okay, there will be no net force on the book. There will be no net force on the book. Okay, due to this normal force and weight reacting as action and reaction. So since action and reaction was acting on the same object, there was no net force. Now we'll take up another example, which is very, very important, and we experience this. See, I was just giving this example, normal force R. You know, this book is giving a force W weight, and the floor also will be giving exactly equal and opposite reaction, that is normal reaction. And see, this normal force, because of this normal force only we feel our weight. Because of this normal force only we feel our weight. Suppose you are weighing your body weight, you just see through, like you just step on some spring balance, some kind of spring balance, and you see the reading, and that reading how it comes, because when you step on that, weight will be acting on this floor of this weighing balance, and weighing balance, that floor also will give equal and opposite reaction to our legs. Okay, and that reaction is exactly equal to the weight of our body. That's why we can stand on the ground or stand on that. Okay, so just by measuring that normal reaction required to apply to balance the weight, so that normal reaction is being noted or recorded in the weighing balance machine and giving the weight. Anyway, so this is an example when you walk. So when we walk, generally what we do, we apply a force, as you can see from here. We apply a force on the ground obliquely, not like this. When you stand, we apply force which is vertically downward, but when you walk, we apply force in oblique manner. See, this is the manner. See, your leg is like this, so the force is applied in an oblique manner onto the ground. So what will ground do? That will do is that it will also apply a force equal and opposite force, that is called reaction. Or see, this is the reaction from the ground. As we apply a force obliquely to the ground will apply an equal and opposite force, which is eventually reaction ground. So reaction of the ground, which will act along the same line. See, along the same line. That's why the force also will be oblique over here. Reaction force will also be oblique over here. If your action is in this way, the reaction will be in this way. Okay. If your action is given like this, reaction also will be like this. Okay. Action reaction will be happening in the same line. Okay. Along the same line but opposite direction. So as you have given the force obliquely, the normal reaction R also you get obliquely. And suppose the normal reaction is making an angle theta with the horizontal. So H is actually horizontal component of the reaction. Horizontal component of R. Okay, and V is actually vertical component of R, similar to this horizontal component. So this is the original vector. Now you have got horizontal component, capital R, cos theta, and vertical component V is equal to V as sin theta. It is actually we have already learned like how to resolve a vector along any direction and direction perpendicular to that. So if your r vector is angle theta, so with the horizontal, so this direction you have to take cos theta, and along the other perpendicular direction you have to take sin theta. Anyway, so in this case, what is important is that see the vertical component r sin theta will actually balance our weight, which is mg. Okay, this will balance our weight completely. So once this is done, then we will be free to move. Now see the horizontal component h is equal to r cos theta. So this component will help us to move forward. This component will help us to move forward. This one, you look, this one, move forward. Horizontal component will help us to move forward. So this is the complicated mechanics happening in every footstep we take, isn't it? So physics is everywhere. So this is about while you walk. We'll take up one more example. See, this is a bullock cart. Sorry, this is horse cart. A person is riding a horse cart. So what is happening? What I'm trying to say here? See, just like our leg, horse while pulling a cart and running, what it does, it actually applies a force in see oblique direction to the obliquely to the vertical direction. Okay, at a certain angle theta, suppose theta, it makes a theta angle with the vertical. It applies force obliquely to the ground. So what ground will do automatically? It will send one reaction force which is exactly equal but opposite in direction. Okay. Now look what happens. This is the r. So if this is theta, this also the theta. So it has two components. One is the vertical component r cos theta and horizontal component r sin theta. Now the question is, what is the role of this vertical component? This one v, and horizontal component this one. So the vertical component will actually balance its weight. Okay, weight or mg. And what this horizontal component do? Horizontal component help is to move forward or help the horse to run in the forward direction, r sin theta in this case. So you should not be sticking to r cos theta is equal to r cos theta itself is giving a force to move forward, and then r sin theta balancing. These are actually everywhere. You have to draw the figure nicely, and then you have to see the components by breaking the or by the use of resolution of vectors, that concept. So these were few illustrations from Newton's third law of motion. Now one more important and very interesting illustration of action and reaction we'll learn, that is weightlessness. What is that? Weightlessness in the lift. Okay, let me tell you once again how do we feel our weight. See, suppose we have a lift we have kept one weighing balance on the floor of the lift, and a person is just standing on the lift. Okay, person is standing on the lift. Sorry, standing on the machine of the lift. So see, along the gravity, its own weight, that is mg, will act, isn't it, towards the downward direction. And at rest, see, now the lift is actually at rest. Lift at rest. At this condition, resting condition, the normal reaction which is given by the weighing balance will act in the upward direction. And eventually, this R and mg will be equal. This R and mg will be equal when the lift is not moving. Okay, and because of this R or normal reaction, we feel our weight. We feel our weight. Okay, now we'll see what is called weightlessness. So yeah, so in this case, R is actually, I'll call R as apparent weight. Apparent weight. So this is called apparent weight. So apparent weight is when the lift is standing, then R is equal to mg. Now we will take up a situation when the lift is moving upward with an acceleration a. With an acceleration a. So in this case, look what happens when it moves upwards. Anyway, this is the mg, which acts through the gravity. This is center of gravity. This is center of gravity g. The weight is acting through that gravity vertically downward, and lift is suppose moving up. Okay, moving up with an acceleration this. So what is the net force at this condition? Net force on the object will be R minus, okay, I'm sorry, this will be net force, which is R, I'm sorry, this net force is actually M into A, because the man is inside the lift, so the acceleration of the man will be the same as the lift. So this is MA is equal to, see, look here, R minus mg. I hope you agree with me. Okay, when an object, sorry, when the lift is moving upward, see, with an acceleration a, so the force, net force, then it will be net force or net acceleration is this one. If I say the man is inside, then the acceleration of the man also will be the same. So the man has a force, net force on himself inside the lift in this condition when moving up with an acceleration a. So I'll just write here, moving, lift moving upwards with an acceleration a. So at this condition, net force on the man will be m into a. This is the difference between the normal force upward and the weight of the object. So this will give you the net force on the object, this man or woman. Yeah, woman. So what is the apparent weight? Apparent weight means you have to find out R. So what is the R? R is actually M into A plus mg. So you can see M into A plus G. Okay. So what does this mean? When a lift accelerates upwards, the apparent weight of the man inside rises. So man will feel his weight to be more. Weight to be more. Okay. So this is so A plus G. Because of this A plus G, actually at resting condition, the apparent weight is R is equal to mg. But in this case, ma plus mg. So it is greater. That's why the man will feel himself heavier than earlier. Now we will take up another situation. Okay, so this is actually moving up. I'll just write in terms of notation. This is R, this is mg. Now, suppose the lift is moving downwards. Now the lift is moving downward with the same acceleration A. So what will be net force? Net force, say here R will be upward and mg will be downward. So what will be the net force on the man? Man will be mg minus ma. Okay. Okay. So this is, I'm sorry, this is mg minus R. This is mg minus R. R is the reaction force, and F net is ma. M into is F net. So in this case, look, if I find out R, R will be mg minus R. Sorry, mg minus ma. I'll just clean it everything. Let me just try it once again. Suppose the lift is moving down. So as you know, the reaction will be acting upward. Weight is moving like weight is downward. So what is the F net? Without any confusion, mg minus R. This will be F net. So F net can be written as m into A. Net acceleration A. So mg minus R. If you simplify, we have to find out what is R. R is mg minus ma. Okay, so which is m into g minus a. So that means the acceleration, see, in the normal condition, R is equal to mg, which is the apparent weight of the object. But what is this now? It is g minus 1, m into g minus 1. That means the apparent weight is less in this case. That's why when, see, we might have this experience while riding lift. When it is moving up, we feel little bit heavier ourselves, and when it is moving downward, we feel less weight, right? So this is called so this is called the decrease in the weight inside lift. Now weightlessness means weight has to be, this apparent weight has to be 0. What is the condition? Look here. Here it was going down, here it was going up with A. This is R, this is G. Here also this is R, this is G. In this case also this is R, this is mg. Mg I should write. Okay. So in this case, you look, if the lift is moving down with an acceleration equal to g. Acceleration equal to g. So in this case, acceleration equal to g when it happens, when it is freely moving, when the lift is freely moving downward direction. So at this situation, what will be net force? Net force. Okay, so net force will be mg minus r is equal to net force. What is the net force? Net force is also mg now. Okay, because g is the acceleration. In place of a, I can write g. So what will be this? Mg minus mg. So normal reaction given by the spring balance on us is 0. That means apparent weight is 0. So apparent weight is 0. Apparent weight is 0. If the apparent weight is 0, because of this only we feel our weight of body. So if this r itself is 0, r, so r means apparent weight is this one. Yeah, r. If the r itself is 0, that means we don't feel any force on ourselves. So at this condition, what is the condition? If an object moving freely in the vertical downward direction, freely in the sense it is always under gravity g, then if the lift also moving in the same direction, downward direction, then what happens? You have no normal reaction or apparent weight. So what you get is weightlessness. That means you feel yourself having no weight. Okay, so that's why it says if the rope of the lift is broken, then what happens? This situation will happen. There will be no weight for us. Okay, we'll be feeling ourselves weightless, and eventually you may not be able to see, like stand on the ground of the lift itself. You will just move up. Okay, so because of this weightlessness. So I'll stop it here. If you have any problem in this part, basically this apparent weight, Deepa, you can ask me now. Okay. Next day I'll take up conservation of linear momentum and many other things, interesting things. So from this weightlessness or motion of lift, from this portion there will be a question sometime. Okay, Deepa, if you have any doubt, you can ask me. The discussion is open for like the class is open for discussion now. You can ask me any question if you have. Do you understand why you feel weightlessness? Because the reaction, sorry, apparent weight will be 0. Okay, apparent weight will be 0. So when a lift accelerates downward, the apparent weight of man inside the lift becomes 0. This is the case for free fall. Okay, so this happens when we freely fall. See, sometimes you look, see, in the skydive, see, people are actually thrown from helicopters. So they have to, before their parachutes open, they have to fall freely under gravity up to certain height. Okay, and at that time, if the air resistance is negligible, then they are actually falling under gravity. Okay. So in this case, actually the lift is having the acceleration is equal to the acceleration due to gravity, because it is freely falling. Okay, so if you don't have any question, I'll stop this session here. I'll give you numerical assignment on this particular topic, and I'll see how you can do.
This conference will now be recorded.